In this goal, we're going to be talking about Graham's law. Graham's law talks about gases effusing. And there's a difference between effuse and diffuse. So when you have diffusion, that is when you have gases mixing into other gases. When you have effusion, you have gases that are leaving their container and going into a vacuum. And there's a little pinhole, and you can measure how fast a particular gas goes through the pinhole into the vacuum. And Graham's law says that at the same temperature, the smaller the mass of the gas, the faster it will go into that vacuum. If you have a large molar mass, then it will go slower through that hole into the vacuum. So Graham's law basically is comparing large mass gas to smaller mass gas. So when the gases effuse into that vacuum space, as I said before, it depends on the molar mass. And we can use this kinetic energy formula. So on the AP test, you won't have to solve for this kinetic energy formula, but it is on your formula sheet so that you can see the relationship. And what this relationship shows us is that if you're at the same temperature, and temperature is a measurement of kinetic energy. If you're at the same temperature, if you have a very, very small mass, your velocity will be going faster than if you had a very large mass, then your velocity would be going slower. So you need to know these two concepts. If your gases are at the same temperature, first of all, they're going to have the same kinetic energy. And then you should know that the smaller gas will have a quicker velocity. So your smaller gas will effuse through that hole a lot faster than a larger gas. And most of the problems on the AP test, it's just that concept. But you can see the kinetic energy formula on your formula sheet to help remind you that because the mass and the velocity are on the same side of the equation, it's an indirect relationship. So as one goes down, the other one will go up, and vice versa. Now, Graham's law takes the kinetic energy formula, and again, if we have two gas molecules at the same temperature, that means that their kinetic energies will be the same. So we can have gas 1 and gas 2, or gas A and gas B, and if they're at the same temperature, they have the same kinetic energy. Well, how can this be where they have different masses? We can derive the equation so that we can put all the masses on one side and all the velocities on one side, and we square root both sides, so we end up with a relative rate. So it doesn't tell us exactly how fast the molecules are going, but just tells how fast they're going in proportion to each other. So this is Graham's law of effusion, and I recommend that when you're doing this formula that you have the smaller gas be gas A. So then when you're taking the square root of the masses, you'll have the larger number on top. And it just makes it so that you end up with a whole number. So let's do a problem. Find the relative rate of effusion for krypton and bromine. So look up krypton on your periodic table. And krypton has a molar mass of 83.8. And bromine, remember it's diatomic, it has a molar mass of 2 times 79.9. 160. So when we look at this formula, first of all, we should be able to answer this question. Which one is going to be traveling faster? And the answer is this one. This one's going to be faster between the two. And Graham's law tells us how much faster. So we're going to take the rate of krypton versus the rate of bromine. And we're going to take the square root of, now it's opposite. So we have B on top now and A on the bottom. So 160 versus 83.8. And we can do that math. And we get that krypton is 1.9 times faster than bromine. So if I have my smaller gas be gas A, then I'm going to get a number that's above 1. But if you actually get a decimal instead of a number above 1, then you know that has been reversed. All right, why does helium leak out of balloons? It's because helium is so small that it actually can leak through latex balloons' porous surface. Some of your mylar balloons don't have porous surfaces, so once you fill them up with helium, then they won't leak out. But helium, it's one of our smallest gases, and so it's moving pretty fast compared to all the gases around it. And it will have more collisions with the side of the balloon, and it will be able to leak out. And once a little bit of helium leaks out, then the balloon doesn't have lift anymore. It will be on the floor. So we have ammonia gas on this end, and we have hydrogen chloride gas on this end. When both of these gases mix, they actually make a solid, ammonium chloride. And here's the question, is the solid going to be formed right in the middle? Will it be formed closer to the ammonia, or will it form closer to the hydrochloric acid? Go ahead and stop the tape and see if you can figure it out. Okay, we're back. You need to know the molar mass of both of these. And so the molar mass of ammonia is 14 plus 1 plus 1 plus 1. So 17 grams. And then the molar mass of this one is 1 plus 35.5 or 36.5. So which of the two gases is going to be moving faster? And that's right, the ammonia gas will move faster. And when you go and do this little experiment, you actually find a white solid form closer to the hydrogen chloride. Looks like I drew my arrows kind of funny. So it's more like right here, okay? So this is where you would find your gas. A little bit closer to the hydrogen chloride side because, again, ammonia moves so much faster than your hydrogen chloride. And you could calculate Graham's law to figure out how much faster the ammonia travels. All right, let's do one more problem. What is the molar mass of gas X if it diffuses 0.876 times as rapidly as N2? Now, this little decimal tells me something. That tells me that they put the N2 mass on the top because I didn't get a number above 1. I got a number below 1. Okay, so I'm going to put my gas X here and my ammonia there at the top. So I have the rate of X compared to the rate of N. And then I have my molar mass of N, which is 28. And I don't know gas X. But I do know that the rate is 0.876. And so that equals this side. And I'm going to get X on its own side. And how I get rid of that square root is I'm going to multiply by, or square it. And I end up that X is equal to 36.5 grams per mole. So this problem's a little bit different, but I can think through it and figure it out, even if they put the larger mass on the bottom instead of the top. When we look at the velocity of the gas, we can look at some distribution charts. These are called Maxwell-Boltzman distribution. And in this first graph, I have the same gas but at different temperatures. So I have the same amount of gas, so the same number of molecules, and I'm comparing them at different temperatures. So what I want you to notice is that the colder it is, then the higher the peak, and that our molecular speed has slowed down. So as the temperature goes down, then my speed or my velocity goes down too. So it is a direct relationship. As I speed it up, as I increase the temperature, you are going to increase the velocity. And what you're going to see is that this curve flat lines. So it gets a little bit flatter. We're going to see that we have some molecules, they stay slow over here. So it's not like all molecules are at the same temperature. Overall, an average velocity, more molecules are going faster at that temperature. I'm still always going to have some that are going slow and some that are going really, really fast. But you can see that as your temperature goes up, more of the molecules are going faster. So it just has to do with those collisions, and you'll have some that are going a little bit slower, but generally, as you increase the temperature, more of the molecules are going to go faster. Now let's look at this second chart. This second chart, the Maxwell-Boltzman distribution chart, again, we're looking at molecular speed, and this time we're looking at the same temperature but different size molecules. And what I want you to see is that the heavier the molar mass, then the slower they're going. So as you increase the molar mass, then you decrease the velocity at the same temperature. So you can see that helium over here is really going fast. Again, you are going to have a distribution, so they're not all going to be going super fast. Some are still going to be going slower, but generally more of the molecules are going to go faster. By the way, the area under the curve is all the same here, so I have all the same number of molecules. So I see that my chlorine, which has really heavy molecules, more of them are going slower. And my helium, which I have very low molar mass, more of them are going faster. So these are Maxwell-Boltzman distribution curves. We're going to see them a lot during the year. So this is just the first time we've seen them. We will see them again, especially when we talk about rates. But you do need to know what these mean and how to draw them. So if I gave you a heavier molecule and then a lighter molecule, you should be able to draw me a chart that looks just like this, with the heavier hanging out at a slower velocity and the faster going flat and hanging out more with increased velocity.